find the substances approximation ABC output for the 4-bit converter. To is a 3.2174 input, is a reference of 5 volt. So the input voltage is already given at 3.2174 volt, and reference voltage is 5 volt. So we have to determine the output digital output. So digital output bit you need to determine. So firstly we make the comparison. Input the IB is at 3.2174 volt, and reference is a 5 volt. So first comparison you have to utilize the equation. So Vf is equal to V reference multiply 2 power minus n. So first you have to utilize the reference voltage. First formula you have to use this formula. So we have to make the comparison. The reference voltage. So this is for the Vf is equal to V reference multiply 2 power minus n. So the first you put the set n is equal to 1. Set n equal to 1. So this one. So V1 means the reference voltage is a 5 volt and 2 power minus 1. So you got the thing that way is a 5 divided by 2 is 2.5 volt. So after you got this 2.5 volt, we compare the input. So input is a Vin. Vin compare with Vs. So the Vin is a 3.217, Vs is a 2.5. So that you can see the Vn is a greater than the Vs. Because Vn is a 3.217, Vs is a 2.5. So when the Vn is a greater than Vs, so V1 is a 1. So long as the Vn greater than Vs, you can take the V1 is 1. So this is for the first comparison. You take the input 3.217 volt, and then this input voltage, and you make the comparison. So you put the n equal to 1. Set the n equal to 1 to the V1. So for the V1 we have to calculate the Vf. Vf is a reference voltage. So this Vf is equal to V reference multiply 2 power minus n. So this is for the reference voltage that influenced by the number of bits. So reference voltage influenced by the number of bits is the Vf. That we can be calculated by the formula V reference multiply 2 power minus n. For the n equal to 1, you have to use the formula Vf equal to V reference multiply 2 power minus n. So that this will be just 5 multiply 2 power minus 1, so you call it 2.5 volt. So this 2.5 volt is Vf. So we compare with the V input voltage and the Vf. So the input voltage is 3.217 is greater than Vf, so V1 is equal to 1. Okay, we got it. And then second condition, you put the set n equal to 2. So the input voltage stays at 3.217 volt, reference is 5 volt. So that for the n equal to 2, you also need to calculate the reference voltage affected by the number of bits. So this formula for the number of 2, we have to utilize the formula V reference multiply 2 power minus n plus V reference divided by 2. So this formula. So that only the first time you have to use the Vx equal to V reference multiply 2 power minus n. But after there's a B1, B2 to the successive bit, you have to utilize the Vf equal to V reference multiply 2 power minus n plus V reference divided by 2. Okay, so this one you can calculate. So V reference, we say that V reference is the 5 volt multiply 2 power minus and this is you set the n will be just 2 bits, so minus 2 plus Vf is 5 divided by 2. So by solving this one, Vf you got the thing is the 3.75 volt. Vf is a 3.75 volt. So that we compare Vin compare with Vf. So the Vin is a 3.217, Vf is a 3.75. So you see that Vn is less than Vf. So Vn less than Vf. Therefore, V2 is equal to 0. So input voltage is less than the Vf, reference voltage, so you have to calculate the V2 is equal to 0. When the input voltage is greater than the Vf, V1 equal to 1. So by this way we make the comparison. This comparison is the input voltage is given to reference voltage, so that this reference voltage is influenced by the number of bits can be calculated by Vf equal to V reference multiply 2 power minus n. So for the V1 you have to use this formula. Vf equal to V reference multiply 2 power minus n But for the bit 2, bit 3, bit 4, you have to use the another formula. Here is going to be reference multiplied by 2 power minus n plus b reference divided by 2. So for the bit 2s we substitute the b reference is 5 and number of base is 2, so that we've got the Vs at 3 by 7.5. So this 3 by 7.5 compared with the Va, so you find that the Va is less than the Vs. So bit 2 is equal to 0. So similarly, we calculate for the 4 bits, so you have to calculate up to 4 times. So that we put in a set n equal to 3. So Vf is equal to C reference multiplied 2 power minus n plus C reference divided by 2. So that we calculate the reference voltage. So reference voltage is a 5 volt minus 2 power minus 3 plus 5 divided by 2. So by solving this answer, you got the Vf is a 3.125 volt. 3.125 volt. Then we compare Va compare with Vs. So Vn is we calculate at 3.217. Vs at 3.127. So you can see that the Vn greater than Vs. So Vn greater than Vs. Therefore, bit 3 is equal to 1. And then finally that you can calculate, this is for the 4 bit. 4 bit means you have to calculate 4 times. So that we have to set n equal to 4. So that we calculate the Vs. So V reference multiplied 2 power minus n plus V reference divided by 2. So the reference voltage are 5 volt. 5 multiplied 2 power minus 4 plus 5 divided by 2. So by calculating this, we call the Vf. So Vf will be 3.437 volt. 3.437 volt. So then you compare Vn compare with Vf. So the Vn value is 3.217. The Vs is 3.437. So that in this case you can see that the Va is less than the Vs. Va less than Vs. Therefore, bit 4 is equal to 0. So after that you can write the bit 1, bit 2, bit 3, bit 4. Bit 1, bit 2, bit 3 and then bit 4. So we substitute. So bit 1 value is 1. Bit 2 is 0. Bit 3 is 1 and bit 4 is 0. So the digital format is 1010. So this is ways we make a comparison. So this is we call it a substitute approximations analog to the digital conversion. So that we set the n value bit 1, 2, 3, 4, 5. So those value and the input voltage are made a comparison. So those comparison the setting is done by the counter made a counting, and those countings are signal and the IC comparator made a comparison and the output coming out. So by this we calculate for this comparison. So we make the statistic approximation method. You use the analog to the digital conversion. So now we also utilize for the digital circuit. So this conversions we can done by the hardware. So this hardware is we got the logic network, digital counter, made the comparison. Those circuits are included to perform this function. So this is we call it RAM analog to the digital converter. So RAM analog to digital converter means compare the input voltage against the linearly increasing RAM voltage. So linearly increasing RAM voltage, you can see here input voltage VA unchanged, but this VS is depending on the reference voltage. Depending on the reference voltage, this voltage is changing. So this voltage will change. Firstly, the reference voltage VA is start from the 2.5, and then reference voltage second position is 3.75, and then 3.1275, and 3.4375. So those voltages are changing. So changing from the 10 to 9, so this is the reference voltage are changing. This changing reference voltage, and then you can compare with the input voltage. So changing means differentiate. Changing. So this function, to get this function, you have to utilize the integrator circuit. So this is for the integrator circuit. So we have to utilize the integrator to get this function. So to get the integrator, you have to utilize for the resistor, capacitor, and the operational amplifier connection. So that connection with I will give them. That is AD converter. Then that AD converter means that you see that this function here. reference voltage VF will be increasing. VF will 2.5 volt, then go to the 3.75 volt. Those voltages will be changing from time to time. So this changing down time to time is we have this flow function. To get a slope function, you have to utilize the integrator circuit. So this is the integrator circuit included in the range analog to the digital converter. The range type AD converter essentially compare the input voltage against a linearly increasing ramp voltage. So this is the function of the range integrator. Okay, so in this case, the range integrator, you can see the things are two slopes. One slope is from the bit 1 to bit 2. Bit 1 to bit 2 is 2.5 volt to 3.75 volt. So this is for the bit 1, bit 2, bit 3, bit 4. So bit 1 to bit 2 is firstly you start from the 2.5 volt and end at the 3.75 volt. Okay, so this is for the increasing like this. After this bit 3 to bit 4, bit 3 to bit 4 is they are going down. Bit 3 voltage is 3.437. 3 by 127 and 3 by 437. So this one is change to this voltage here. So then this is 3.437 and this one will use 3 by 127. This is 3.127, 3.437. So this is a change. Bit 1 to bit 2 is increase and bit 3 to bit 4 is also the change. So you see the two slopes. Two slopes means this is we call a dual slope function. Dual slope function. Dual slopes are the integrator circuit. So this is we call it a dual slope range is analog to the digital converter. Dual slope integrator circuit. This dual slope integrator circuit and the input voltage are made the comparison and then we can produce the output. So this is we call the dual slopes are AD. Dual slopes are converter. Then there's a successive approximation method. So we increase the bit. So the VF value will be changing. This VF and the input voltage are made a comparison. So this comparison and the output voltage are coming out. Output voltage are coming out. For the VN is greater than VS, bit 1 is 1. VN less than VF, bit 2 we got the 0. So we coming out like this. So that kind of things is we can utilize for the range analog to digital converter. Dual slopes are analog to digital converter. So analog to digital converter dual slope we utilize. The input signal to drive the integrator for a fixed time C1. So that we generate the output voltage V1 is equal to 1 by RC, the integration VHDT. So that V1 is 1 by RC multiply C1 multiply V8. So this is for this integrator circuit. So this integrator circuit is driven by the input voltage. So that we draw the circuit diagram for this circuit. This is for the dual slopes analog to the digital converter circuit. So the input signal to drive the integrator for fixed time C1. So output voltage V1 you can calculate. So this integrator circuit is the integrator circuit, resistor, capacitor, and the IC. We connect like this. So this is the integrator circuit. So this integrator circuit is the operational amplifier. Operational amplifier, integrator circuit. So this integrator circuit you can calculate. V1 is equal to 1 by RC integration VHDT. So the therefore is the input 2 voltage. So reference voltage and the any voltage are made a comparison by the relay. So these relays are the input signal passing through the integrator and then they passing through the comparator. So that this function is that we are compared with the reference signal and there's a digital counter the count is a bit output. Then this digital counter we connect it with logic network and these logic networks are activate the relay. So now as this one activates to the way outputs are coming out. So this logic network we initiate the relay when the counter starts and this will stop when the conversions are completed. So this integrator circuit is utilized for the analog to the digital conversion. So by using this circuit, this program is that we compare the input voltage and the reference voltage. So reference voltage influenced by the number of bits and the input voltage are made a comparison. So this comparison and the bits are coming out. So this programs are performance if the physically executed by this comparator circuit. So this is we call it analog to digital converter circuit. DC. So dual slope ADC shown in the figure. So this is the figure. We can start the counting. So This is for the US low ADC. So this is the T1 and this is T2. So T1 is increasing and T2 is decreasing. So this is for the start counting. Start counting. Here we is the stop counting. Counting starts at here and the counting stops at here. So this is T1 and T2. So the T1 and T2 altogether are T1 is altogether 10 milliseconds. Phase integration time is at 10 milliseconds. The resistance value is 100 kilo ohm, capacity 0.01 microfarad, and so reference voltage is at 10 volt. The phase integration time is 10 milliseconds. So we have to find the conversion time for the 6.8 volts input. So the formula we can calculate is, this is the V1. V is equal to the 1 by RC, T1 multiplied V8. So this formula. V is equal to the 1 by RC, so T1 multiplied V8. So that firstly we have to calculate. So in this case, the input is at 6.8 volt, and so T1 is only given as 10 milliseconds, and resistance value is 100 kilo ohm, capacity 0.1 microfarad. You can calculate this voltage V1. So V1 you can calculate. So this is a 1 divided by resistance is a 100 into 10 power 3. The capacity is a 0.01 into 10 power minus 6. And the T1 is a 10 milliseconds. So this is a 10 into 10 power minus 3. And the input voltage is 6.8 volt. So we substitute 6.8. So by solving this one, you got a V1 and also you got a 6.8 volt. So V1 you got. After you got the V1, you also need to find a conversion die. So there, in this case, we have to find a conversion die. So the conversion die formula is this one. TH is a conversion die. So conversion die is equal to P1 multiply V1 divided by V reference. So this is two equations. First equation, we can find the V1. V1 is equal to the 1 by RC multiplied with T1 into V8. And after that you got the V1, you can find the conversion die. Conversion die formula is T1 multiplied V1 divided by V reference. So here we only got the T1 value. The T1 is at 10 milliseconds. 10 into 10 power minus 3. And V1 is at 6.8. And reference voltage is given. So reference voltage is a 10 volt. So by solving this one, you also got the same way here, 6.8 milliseconds. So conversion time is 6.8 milliseconds. So this is the calculation of the US load indicator circuit. Okay, we can calculate that voltage V1 value and the conversion time value. So this generator US load indicator circuit also got the characteristic. The input is at a common level voltage. We have to give it 0 to 10 volt or 0 to 5 volt or the minus 10 to plus 10 volt. Output will be the parallel or the series by the watt. The coming out from the output. The reference is a stable and the low repairs source is important. Power supply is we can utilize the dual power supply. Plus or minus 12 volt or plus or minus 18 volt is required. Digital signal is the ADC usually provide the high levels on another line. So those are the characteristics of the general characteristics of the US load ramp indicator circuit. The characteristics. So the general characteristics of the ramp analog to digital converter. The input is a common level 0 to 10 or 0 to 5 or the minus 10 to plus 10 volt. Output will be the parallel or the series binary watt. There is the encoding of the analog input. The reference will be the stable and low repair source against which the conversion is performed. The power supply will be generally a bipolar plus or minus 12 volt to plus or minus 18 volt supply is required for the analog amplifier and comparators and a positive 5 volt supply for the digital circuitry. The digital signal is that the ADC usually provides a high level on another line as an indicator. So those are the general characteristics of the US load ramp analog to the digital converter. Okay, so this is the circuit, the temperature measurement. So the measurement of temperature using a sensor. The sensor output is 6.5 millivolt per degree centigrade, must measure to 100 degree centigrade. So that this sensor is a temperature measurement we utilize this sensor. So the sensitivity is 6.5 millivolt per centigrade. They must need to measure with 100 degree centigrade. So in this case, we use a digital gate. So 6 bits analog to digital converter is utilized, and the tempo is a reference. So the first thing you need to develop the circuit. So develop the circuit means that input signal. So this is one here, negative positive. So this one is a VIN. So this is you put it on. This one is a reference voltage. So this voltage R1 and the RF. So this one with the V reference. So this is VR. So this is the digital circuit. So the reference voltage is given at the R1 and the RF. R is the forwarding and this is the outgoing out. So this is the circuit. So in this case, we have to calculate the gain. So this is the gain need to be calculated. To design a circuit, you have to find the ratio of the RF and R1. So ratio of RF and R1 is the gain on the circuit. So gain on the circuit you need to calculate. The gain is equal to RF by R1. So if you know that gain, you can put the R1 value and then you can calculate the RF value. So this is the thing that you have to calculate the gain. So to calculate the gain also got a formula. The gain formula is equal to V out divided by Vin. So this is the formula to calculate the gain. So the Vin is we already know. So Vin value is as so V out we have to find. So Vin is here 6.5 millivolt per degree centigrade. So this is the sensitivity. You need to measure the tempo. So then you can calculate the Vin. Vin you can calculate. So volt per degree centigrade multiply the voltage to measure. So volt per degree centigrade multiply voltage to measure, then you can calculate the Vin. So the volt per degree centigrade is 6.5 millivolt. 6.5 into 10 power minus 3 millivolt per degree centigrade. Then the voltage is you have to measure the tempo. So this is for the, and in this case the temperature to measure the 100 degree centigrade. So temperature to measure. So 6.5 the volt per degree centigrade multiply temperature to measure. So that volt per degree centigrade is 6.5 into 10 power minus 3. Temperature is 100. So this becomes by solving this one, the voltage will be there 0.65 volt. So this is for the input voltage. Input voltage you can utilize because of the problem is given. The sensitivity is 6.5 millivolt per degree centigrade. We need to measure the temperature at 100 degree centigrade. So the Vn is formula is volt per degree centigrade multiply temperature to measure. So the 6.5 into 10 power minus 3 multiply 100. So we call it this Vn is equal to 0.65 volt. So this is Vn. Vout is the digital output. So the Vout formula. The Vout formula is we can calculate. Vout formula we use Vr multiply the formula we use A1 into 2 power minus 1 plus A2 into 2 power minus 2 plus A3 into 2 power minus 3 up to that. So this is for the 6-bit system. So you can add up to A6 into 2 power minus 6. So this is it. So that we assume that all bit 1, bit 2, bit 3, bit 4 are 1. So we assume that this is A1 equal to 1, A2 equal to 1, A3 equal to 1. Up to A6 equal to 1. And therefore we can calculate VR is equal to VR multiply 1 into 2 power minus 1 plus 1 into 2 power minus 2 plus so 1 into 2 power minus 6. So that we substitute here. So reference voltage already given. Reference voltage is already given a 10 volt. So this is 10. Multiply 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus 1 by 2 power 4 plus 1 by 2 power 5 plus 1 by 2 power 6. So by solving this one, you got the thing with there 9.84375. 9.84375 volts. So this is for the we can calculate the VR. After you got the V out and the V in ratio, we will be able to calculate the gain. So we substitute the gain formula. Gain is equal to V out by V in, so that you can calculate the gain. After you got the gain, you can get the ratio between the RF and R1. So that then you can assign the appropriate resistance to the circuit. RF by R1. But RF is a combination of the R1 and R2. So the RA is a 15.14. So we got the ratio. So this is the R1 plus R2. So you can have to select any value of R1. So that we set R1 is equal to 1 kilo ohm. Then you can call that R2. 15.14 is equal to 1. So this one is a 15.14. So if you put the R1 in 1 kilo ohm, so this will be the RS also 15.14 kilo ohm. So this is R2 you can calculate. So R2 is equal to 14.14 kilo ohm. So this ratio. So you can put the R1 equal to say 1 kilo ohm and the R2 14.14 kilo ohm. So this circuit way you go like this. So this one will be the R1 the 1K. And then this one will be the R2 14.14K. Then you got the V out. So this one is the V in here. So this is V reference. So this is by this way we can calculate the analog digital converter circuit. So this is the temperature measurement sensor. So in this case we utilize analog digital converter circuit for the sensor circuit. So this is the input is the analog signal. The analog signal is coming out. So we use this one as a sensor. So this is typical construction. Okay, so this is we calculate the rate gain. So this is for the first part. And second part, we also need to determine the temperature resolution. So temperature resolution means the sensitivity. So how to calculate the temperature resolution? The equation to calculate the temperature resolution is temperature resolution delta T is equal to delta VT divided by voltage per degree centigrade. So this equation. So the temperature resolution. So the equation with the delta T is equal to delta VT divided by voltage per degree centigrade. So this equation. Delta VT divided by the voltage per degree centigrade, you call it the temperature resolution. And also, in the meantime, you also calculate the delta VT. So voltage per degree centigrade is already given. Voltage per degree centigrade is the formula is given as 6.5 millivole per degree centigrade. So you have to calculate the delta VT. Delta VT need to be calculated. So delta VT formula is, we also use the delta VT formula. So delta VT formula is delta V divided by K. So this is another formula. And also delta V also you can calculate. Delta V is VR multiplied 2 power minus n. So this is the variance of the voltage. Delta V is the change of the voltage. So the change of the voltage you can calculate by the formula. Input the reference voltage multiplied 2 power minus n. N is the number of bits. And delta VT means the change of the voltage affected by the temperature. The change of the voltage affected by the temperature can be calculated by the formula is the delta V by K. After this, you got the delta VT, you can calculate the temperature resolution delta T. Delta T is to delta VT divided by 4 per degree centigrade. So this is the three steps we have to calculate. Okay, firstly we calculate for the delta V. So reference voltage already given, reference voltage is 10 volt. So number of bits is 6 bits. So the delta V is equal to VR multiplied 2 power minus n formula we calculate. So delta V is equal to VR multiplied 2 power minus n. So delta V is a VI stable 2 power minus n 2 power minus 6. Then you got the delta V. Then delta V we calculate is the 0.15625 volt. 0.15625 156,254. So this is the delta V. After you got the delta V, you can calculate the delta VD. So delta VD is equal to delta V divided by J. So the delta V is at 0.15625. So alright, J. So J is at, we already calculate, J is at 15.14. And you can calculate the delta VD. So delta VD will be the 0.01024. 0.010124 we got. After you got the delta VD, you can calculate the delta T. So delta T is equal to delta VT divided by 4 degrees centigrade. 0.01012 divided by 4 degrees is 6.5 into 10 power minus 3. So by this way that you can calculate the temperature gain if we were at 1.59 degrees centigrade. So we got the delta, so delta T. So this is the temperature that resolution we calculate. So this is for the second part of the problem. Okay, finally we design this circuit. So the input is a sensor. Since input sensor is the 6.5 millivolt per degree centigrade transducer. Then this one is connected to this one. So this circuit you have to calculate the gain. By using the operational amplifier circuit, we can design the gain. So this is for this circuit, negative positive. So this is negative. Today, 14.14 kilo ohm. So this one is connected to here. So this is 1 kilo ohm. So V reference. So this is the VN. And then this one is this one output here. Then we utilize this analog to digital command, ADC. So ADC you get this 10 volt reference. So then we coming out the 6 bit. So this is 6 line. So 1.5 volt. So this is 6 bit output coming out. So this is for the so that's the design of the circuit. So input will be a transducer. Transducer's sensitivity is 6.5 millivolt per degree centigrade. After that we enlarge the gain. So this gain is an analog signal. So this analog signal is you convert it to digital by digital converter. Digital converter we use for this circuit, then it's analog digital converter. So that kind of circuit we utilize. The output will be the 6 line coming out. 6 line coming out is the 6 bit output. So in this case, this digital converter require the 10 volt reference. So this is to the design of the sensor circuit. So this project, so this is digital approach, and this is the final design. The microprocessors are compatible with ADC. So we utilize a microprocessor. So those the analog to the digital converters are here. You can coming out the bit. So those bits are the parallel data. You can feed the digital data into the microprocessor. So the these microprocessors are connected to the data bus. So they are also connected to the input output decoding circuit and memory circuit. So those things are the connection between the interfacing with the transducer and the analog to digital converter and also the computer. So I give you this overview diagram. So by this is this data output is a digital output. This digital data output you can connect it to the computer. So input is a transducer here, transducer, and this one was the K circuit. And after that, analog to digital conversion circuits we utilize the RANS integrator circuit, US12 RANS integrator circuit. So output is a bit line. So output bit lines you can fed into this microprocessor circuit. So by this way you can construct a computerized control system. So this is the overview diagram I will draw. So this is for the microprocessor compatible ADC. So microprocessor, this is the analog to digital converter. So this ADC system. This one is that we connected to the reference voltage and VA. VA is really the transducer and this gain circuit. So here we can the ADC connected to the memory and also this one output. So this output is connected to the input output decoding circuit. After this reference coming here, so this is a output we connected to the input-output decoding circuit. So decoding circuits are connected to the two bus bars are connected to the microprocessor. The microprocessor and we connect to the data bus bar. So this memory decoding connected to the data bus bar. So this is for the microprocessor, microprocessor, memory, input-output decoding, and the ADCs are the assembly circuit. The whole line of the ADC having a W, then interface easily with the microprocessor face the computer. So the ADC have built in the tri-state output. So these ADCs are we utilize the tri-state output. Tri-state output means that we can use the enable signal. So similar to the star circuit, we get the gate firing, so it's the star we conduction. So this is the enable. Gate firing circuit is similar to the enable command. So they can be connected directly to the data bus of the computer. So the data from the ADC is only based on the data bus line when the computer issues and appropriate the enable command. So that by this way we can control the microprocessor. By controlling the microprocessor, the computer can provide the enable command. So when the computer provides the enable command, the ADC place the data onto the data bus. So this is the way that we can control the ADC. Normally the ADC does not have any internal control, so that we have to utilize the ADC. So standard ADC need to be enabled. So this enable signal is provided by the microprocessor computer. At this system, we got the data input. So data inputs are we include the address bar. Address bar means you can allocate the data into the particular address. Decoding system, interface circuit, and reference for the computer. So these are included in the data input system. And another one is the sample force system, because the analog signal is ever changing, so that we cannot start looking at the signal all the time. So the only significant value of the signal is recorded and they are whole. So this is recorded and whole means that the analog sample and force circuit. So sample and force circuit is that consists of the capacitor. So that when the capacitor is charged, capacitor store the energy. So that this data are relevant to the electric charge are relevant to the input signal can be stored in the capacitor. So this is a sample and force circuit. So sample and force circuit is utilized in the input signal system. And so that this data acquisition system we can utilize a 8-bit binary number. 8-bit binary number can be transferred within the 2 microseconds. And also we utilize the interface. So interface means that we have to utilize the amplifier. So appropriate operational amplifiers are also included in the circuit and to write the program. So those systems are for the sample and force circuit, data input board, interface are included for the data acquisition system. So I give you the note for those systems. For the sample and force circuit, so sample and force circuit we use the PFS transistor, and this is capacitor, and this is operational amplifier. So when the FED is driven to the open state, so FED we give the gate firing signal to FED with the conduction, so the FED we charge the capacitor. So the capacitor charge to capacitor retain the depth value. So before the open state of FED occur, so next open before the occurrence of the next open state, this capacitor will hold this charge. So this is by this way that we use the sample and force circuit. So this sample and force circuits are utilized for the data acquisition system. So the data acquisition system will compose of the binary input. So computer can control the many variables. We use the variable we control, so that we have to utilize the programs to control operation. So this means that computer will take the sample, evaluate and the output. So are the programs that control operation. And functions are usually include the amplifier. So operational amplifiers are required. So also the interface system, we write the program. Program required to put together an interface to the computer for the process application. So I now give you the interface system overview diagram. So input with the computer address line. So address decoders are utilized, and also the analog multiplexer. Input can be the analog signal can be coming from the tablet line. So that those lines are need to be the multiplex. So analog multiplexer and the analog decoders are need to interface. After that, those signals are they send to the operational amplifier, and then they send to the analog to digital the converter. And this analog to digital converter they control the output latch. Then the output latch connected to the computer data line. So this is called the data acquisition system. So I give you this data acquisition system diagram. Okay, this is the data acquisition system. So data acquisition system, you can see that inputs are analog signal. So analog signal can be coming from the multiple input. In the process system, some signals are related to the temperature, some is for the pressure, some will be the speed like this. So those things are the ticket from the transducer. So they fed into the analog multiplexer. So the multiplexer, if we want to only say one line, so this is for the multiplexer we utilize. So this multiplexer output will be one line. So this multiplexer is we connected to the amplifier. Amplifier connected to the analog to digital converter. So those bits are they are coming out. Those bits line coming out. So this is the output data length. So this ADC also be connected with this circuit. So they enable so that they are coming out the computer data line. Similarly, the address encoder is also connected here. This address decoder is that we put the address in. So address is a data-minded. So computer data-minded address so that both signals can be put into the address. So the address is data-minded by the address decoder. So we read that signal and they put into the output flash and they can put into the data computer data line. So by this way the address decoder can select the appropriate data line to put the data. So this is for the data acquisition system. So the data acquisition system access the input from the computer via the address line. The module access the number of analog input. The computer select any one of the channel under the program control for the input data. So this is for the process control system we use the data acquisition system. Okay, this data acquisition system we use the analog multiplexer. So analog multiplexer is called the starter switch. So those switches are the control binaries this is output. So this is analog output. So those switches are controlled by the data selector. So this is the data selector. Switch selector. So this switch selector selects the analog. So this switch selector is connected from the address decoder. So from address decoder. So we use the analog address decoder so that this switch can select the data and can put onto the line. So that in the data acquisition system, the components required are the amplifier. So amplifier, we got the variable gain amplifier, it's required, and also the analog to the digital converter also required, and sample full circuit is also required. And also they are the compatible to the computer. The data module designed to work only the one model or the one type of the computer. So that kind of the data acquisition system is depending on the computer type. When you change the computer type, everything also be changing. So because of this one, their performance are that they controlled by the hardware programming and the software programming. So hardware programming that you can select the appropriate selection of the amplifier gain, differential amplifier. So you have to adjust the differential amplifier gain. By this way that you can use as a jumper. Use a jumper and a pin. This is for the hardware programming. Software programming is this is a high level language. High level control language utilized for the data bus and data modules. So this is for the programming. So hardware programming and the software programming are also requirements to control the process control data system. Digital signal. We utilize a variable data amplifier. So and also we use the ADC